That's not me.
I did.
Okay, that's one.
Oh, yeah, Charles, are you going down with Discord if Bill does the?
Okay.
I don't know what
Are we rolling?
I have no idea.
Okay. So here's the story. So this is gonna form the basis, Charles, of the lecture today, and then we're gonna finish this up on Monday. So this is one of the most important concepts in terms of terminology and how things fit together. So this is what's known as a pressure volume graph. So it's weird because it's like a two-dimensional graph with pressure and volume, but you can also always find temperature that goes with it, mainly because of the fact that you have PV equaling nRT. So what this allows you to do is keep track of the relationship between pressure and volume as a gas goes through different situations. So here's the story. So we're going to have 0.1 moles of gas, right? Okay. 0.1 moles of gas isn't very much. That's like 2.24 liters, which would be like, if you've ever seen like a 2-liter bottle of pop, that's about what that would be, which was going to be, in this case, 0.1 cubic meters. So I've got the volume here along the x-axis in cubic meters. I've got the pressure here, and this is like times 10 to the second. And I got 2.44 times 10 to the, actually times 10 to the third newtons per square meter. So here's what you're told. You've got 0.1 moles of gas at a temperature of 20 degrees, which is about room temperature. It has a volume of 0.1 cubic meters, and I want to know what the pressure is going to be. So all of these are brought to the idea PV equals nRT. So Connor S., I need to find the pressure. So what am I going to do?
You're gonna move volume over to the other side.
Okay? So I'm going to move the volume over here. So I've got 0.1 moles. My R value is going to be that 8.314 joules per mole Kelvin. Don't memorize that. I will always give you that. If you want to store that into your calculator as an R value so you don't have to retype it every time, that's cool. But it's always going to be 8.314. Oh, that's up to you. So now, Scooter, I have a temperature of 20 degrees Celsius. Hi, Mr. Bugby. So what am I going to do with 20 degrees Celsius?
Convert it to Kelvin.
By doing what?
Add a 273,
Which is going to be
293.
293. So 293 Kelvin. And then I'm going to divide that by the volume of 0.1 cubic meters. So basically these cancel out. So somebody take 8.314 times 293.
2,436.
2,000 what?
436.
So 2.44 times 10 to the third newtons per square meter. Now, that's actually, it sounds big, but that's actually a relatively low pressure, because if you consider normal atmospheric pressure is 101,000. Okay, so that's normal atmospheric pressure. So this is why that tennis ball worked, or that ping pong ball shot out. That's like equivalent to 14.7 psi. That's normal pressure. So when I punctured that into that tube, that roughly had about 1 square inch. So basically you had this weight of a bowling ball of air rushing into that opening. That's why it accelerated that ping pong ball so quickly, is because you had the weight of Hank under normal pressure pushing and rushing into that tube. So that's good enough. May South people, I know you guys got to go. Hold on to that number. We'll continue this on Monday. You have no homework over the weekend.
That's what I want to hear.